Hey guys, now we're going to do the free response section here. So on number 10, there's just one problem. I thought I'd try to make it pretty easy. This is a pretty overarching problem. There's a lot of other sub questions that I could ask, and I have asked in the quiz in the past that I probably will ask again on the test. I just want to make this pretty quick. So the table below shows the life expectancy for white males in the United States every decade during the last century. So one would be the first decade of the last century, which would be 1900 to 1910. Two would be the second decade past 1900, which would be 1911 to 1920, et cetera, et cetera. So this is just numbering off the decades. It's just a little bit easier than putting 1900, 1910, 1920, et cetera, et cetera. Okay, so life expectancy is shown here. So you can see, wow, just from looking at the data, it looks like it's going up. It's always going up, but we want to see if there's any curvature in it or anything. So the best thing that we can do to actually visualize the data would be to graph it out. So we're going to go to Stat, Edit. I'm going to put in the decade for the list 1 and just go 1 through 11 there. And then the life expectancy we'll put in list 2. Clearly we're doing, because if we have any variable that's time related, it's going to be our explanatory variable most of the time. Most of the time. And then our response variable is going to be whatever we're trying to measure or that we're interested in, which is going to be the life expectancy. So that's going to be our dependent variable or our response variable, as we like to call it. So let's graph a scatter plot. So second y equals, I'm going to turn one on. I'm going to go from list 1 to list 2. So list 1 to list 2, and then hit zoom 9 to do stat plot. And I've got these models here that are turned on. I'm going to turn them off and then go back to graph. Okay, cool. So if we look at that, it looks more or less like it's linear, but you can see there's some curvature in it, which is going to show up better whenever we run a linear regression and graph the residuals. All right, so sketch scatter plot, did that. Next thing is create a model to predict the future increases and for life expectancy. So to do that, we're going to go to Stat, Calculate, fourth option for linear regression. We're going to go from list 1 to list 2, and then I'm going to store the regression equation under variables, y variables, function, y1, and then hit calculate, and there we go, we've got that information. I've already put it here, so we don't have to worry about that. If we hit graph, it'll actually graph it there because it turns it on automatically, which is what we have here. Now, our model, our A is going to be our slope, which is the 2.5382. Make sure you give me enough decimals. I graded your quizzes, by the way, so some of you guys just did like 1 decimal place, and then but we want to have some more precision. So at least 4 significant figures, significant sig figs. All right, so the predicted life expectancy, is why it's got the hat on the top of it, is our slope times the decade, which is our response variable. It's decades since 1900. As long as you clearly label it in the graph, you don't have to be that precise, I don't think, in the model, plus our y-intercept, which is our b of 50.362. Okay, cool. So sketch the plot of the residuals. Anytime we run a linear regression, it automatically updates the list of the residuals. So to sketch that plot, we're going to do list 1 to the residual list, which is going to be under second stat, which is the list option. On the very bottom is our residuals, and then you can hit zoom 9 again, and there's our residuals. Clearly there's curvature in it, and if we have any pattern in the residuals, it means that our data is not actually linear. We're trying to fit a linear model with curved data, which isn't going to work. It's like trying to fit a round peg through a square hole. So we just need to find a square hole for the square peg, et cetera, et cetera. So is our model appropriate? No, because there's a pattern in our residual plot. So it's curved. We need to re-express it. All right, so sketch scatter plot for the re-expressed data by taking the log of the decade. So usually we re-express the response variable, but this time I wanted you to do the explanatory, so not that big of a deal. So we're going to take the log of list 1 and store it as list 3. So I'm going to go to Stat, Edit, and then for list 3, I'm going to define list 3 as the logarithm of list 1. And then hit enter. So we got that. So that's our new X list, so don't get confused. So now we're going to go from list 3 to list 2 for our scatter plot. So graphing that out. So list 3, so second 3, which is our logarithm of the decade, to list 2, which is just our regular life expectancy. We didn't re-express that. And then hit zoom 9. Okay, something weird's going on here. Let's see what I do. List 3 to list 2, that looks correct. Let's try it again. Zoom 9. Oh, okay, cool. I don't know what happened there, but I am going to turn off the old model because I don't need it. and then hit graph again. Okay, cool. So that's our new graph of the data here. It looks straighter, but to see if it's actually straight, we need to compare it to a model. I don't think I have the model on this one. So to get the model, we have to run a linear regression, which of course is the next thing I'm going to have you do. So go back to stat, arrow over to calculate, linear regression. We're going from our re-expressed decade, log of decade, so that's list 3, to list 2. I'm going to store the regression equation under y2, so I don't save over the y1, just in case I wanted it later. And then I've got all the information here, so no big deal. Hit graph again, and you can see, okay, that looks really straight compared to the straight line, right? But the best way to compare it is to look at the residual plot. So go to second, y equals, and that's why we always graph the residual plot. Our X list that we're graphing is going to be the log of the decade since 1900. So we are going to leave that as list 3 instead of doing back to list 1. So because it's re-expressed, that is what our explanatory variable is now. But our Y list is going to be the residuals. So do that whole thing we just did before. Then zoom 9. Okay, wow. What's amazing is now there's no more pattern in the residuals. Now before we had a clear pattern. Now we no longer have that pattern. It's pretty well randomly spread. So since there's no pattern, that means that we were successful. Our re-expression was successful. We removed the curvature, and now we have a linear data to go with our linear model. So around a hole for our round peg or whatever, however you want to look at it. Okay, so when we write the model itself, make sure that you show how you re-expressed it. So if you re-express the life expectancy, put the log in front of the response variable. If you're re-expressing with the logarithm the explanatory variable, which we do rarely, but on occasion, then it's the logarithm of the decade there. So good to go. Then, of course, we want to use our new model to estimate the life expectancy for white males from 2011 to 2020. So that's actually going to be the 12th decade since 1900. Since the last century is one way of saying that. So we're going to plug in the logarithm of 12. So it's not just 12 into our equation. Remember, it's a log of 12 because the calculator didn't know that we did the logarithm first. It just took data itself. So we need to plug in the log of 12 into our equation, which is kind of odd, but that's why we're doing it now, so that you have some practice. So we're going to go to variables, y variables, function. Remember, it was y2. So I'm going to take y2 and evaluate it at our x value, which is going to be the logarithm of 12, whatever that value is. I said 12. There we go. All right, so that's 75.92, and that actually makes sense. So we're expecting from the years 2011 to 2020, the life expectancy to be 75.92 years. Okay, no big deal. And we don't have to actually do like 10 to the power of anything because we're not undoing a logarithm. We're just applying the logarithm in with the x value, which is pretty simple. All right, calculate the residual. If the actual life expectancy was 78.9, which I looked it up, that's actually the current life expectancy for white males. So in America at least. So the residual is equal to the actual minus the predicted. So the actual we said was 78.9 minus the predicted, which was 75.92, which would give us a difference of a positive 2.998. So the current life expectancy for white males in America is higher than what we would have predicted based on the data that we had before, which is interesting. Okay, cool. So I'm pretty sure that's it. Yes, that's it. There might be other questions I asked, like for instance, analyze the correlation, the strength. What does the correlation tell us? The coefficient of determination, so 98.5% of the variation, and the life expectancy can be accounted for by the model with the log of the decade since 1900, stuff like that. So make sure you still know how to answer those questions. Is it appropriate if we extrapolate? Remember, this was extrapolation and we were off. The model was off clearly. So it's never appropriate to extrapolate unless you're dealing with a natural law of physics or something like that. If it's markets or something, or even life expectancy, we don't know. Like World War III could have happened or something like that. Well, clearly it didn't, but something could have happened that would have lowered the life expectancy drastically. So we don't really know. So you got to be really careful about extrapolation. So anyway, just mention stuff like that. And under 10 minutes, I'll see you guys later.